So we are streaming now.
Okay. Sorry, we are just setting up. We just need 2 minutes still. Thank you.
Yes, no problem. So until we set up, let us introduce ourselves.
Hello, my name is Manfus and I'm a student of the second high school of Ελληνογερμανική Αγωγή.
My name is Manolis Kanyotakis. I am a physicist from the R&D department of Ελληνογερμανική Αγωγή. Together with our colleagues from the University of the Free State, South Africa, together we are going to do a live demonstration of the Eratosthenes experiment. We will be waiting for a couple of minutes before we begin. Okay. The schedule is as follows. We will start with a short introduction of ourselves. Then we will present briefly the theoretical, let's say, and historical framework of Eratosthenes measurement. And then we will proceed to the measurement. You can see that we have already our setups ready. And we will do the measurement this way. So, Lucas, whenever you are ready. Together, we have students from the Ελληνογερμανική Αγωγή School in Pallini, Greece, students from the first class of senior high school. Say hello. Hi. And we have also, together with us, students from Bloemfontein, South Africa, in the Naval Hill Planetarium, who will be also working with us. Hello, everyone. So we wait for a couple of minutes.
Yes, good day. Sorry, we are just sorting out still a couple of technical issues. But yeah, this is Lucas Erasmus, live from Bloemfontein with couple of like 25 eager students today. So yeah, we'll be up and running within the next few minutes. Yeah, please be patient with us. Thank you very much.
Thank you. Okay, so Lucas, I think that we should start our introduction. Let's say, whenever you're ready, we would like to hear more about you, your team, the University of the Free State, a few words, and then we proceed to the presentation. Okay. 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 Allow me to see if I can share my screen in the meantime.
Yes, you can share the screen.
So, should we begin?
Yes, we can begin. We are just waiting for technical issues, but the people on this side is already explaining to the students how it's going to work for the measurement. So you can begin on that side.
Okay. Before we begin, let me summarize a bit the schedule for today. Okay, we will start with the theoretical presentation, as we said, and with the first measurement of the distance between Bloemfontein in South Africa and Pallini in Greece. After that, we will proceed to the explanation of the experimental setup and to the demonstration measurement, which will be done from our South African colleagues. After that, we will proceed to show you, give you the data of a recorded measurement that we did on Thursday, because the weather conditions right now are not favorable here, as you can see, unfortunately. And using this data, we will guide you step by step in order to take the measurement. In the end, we will have a discussion, and we will be able to discuss more about the impact of Eratosthenes in our, let's say, understanding of our world, and also potential sources of error and beyond that. So, Manthos, I think that we are ready. The floor is yours. Okay, let's see what this guy did.
So thank you very much. I'd like to talk about Eratosthenes. Eratosthenes was a great mathematician that lived thousands of years ago. He had a very simple yet insightful idea that led to a significant discovery. He was the first to measure the circumference of the Earth with great accuracy. So, using only a stick and some elementary Euclidean geometry, he would measure the Earth's circumference, as I said. More information about him, let's say, or some, some preliminary questions. What is the shape of the Earth? How big is our little blue dot? Who was the first to measure the Earth's circumference? I think everyone has wondered about these questions sometime. Eratosthenes of Cyrene. Eratosthenes of Cyrene was born in 276 BC in Cyrene, Libya, and died in 194 BC, Alexandria, Egypt. He was a great astronomer, geographer, mathematician, and poet, and he was the director of the Library of Alexandria. He was the first person who devised a way to measure the circumference of the Earth. As I said earlier, about the measurement, 200 years ago, a scroll reads Eratosthenes stating that during the summer solstice in June the 21st, as we know, the rays of light illuminated the bottom of a well in scene. So one person that could go above in a well in seeing the ray, he would see the sun directly above him. So that meant that the sun rays were coming parallel to here. The great polymath started pondering. He knew that if he mounted a stick vertically to the ground at the same time, and the same day in the city of Alexandria, he would observe a shadow. Could this possibly be a way to measure the circumference of the Earth? Yes, I want to say that the sun rays were coming perpendicular. Yes, the sun rays were coming exactly perpendicular to seeing. But in Alexandria, we could measure an angle between the sun rays and, let's say, a stick. So Eratosthenes wanted to measure this angle theta that would allow him to tell what the radius of the Earth is, and as a result, the circumference. Some preliminary assumptions we can make. Of course, the wrong assumption is that the Earth is flat and the sun is very close, so the solar rays will diverge. If I place similar sticks in different places of the Earth, I will measure different shadow lengths. As it is known, the Earth is round and the sun is very far away, so the solar rays are coming parallel to each other as they reach the Earth. If I place similar sticks in different places of the Earth, I will measure different shadow lengths. How do we know what the sun rays are coming parallel as they reach the Earth? The answer had already been provided by Aristarchus of Samos. In the first quarter moon, the angle between the moon and the Earth is almost 90 degrees. The Earth-Moon-Sun angle is also by definition equal to 90 degrees. Thus, The solar rays that reach both the Earth and the Moon are parallel among them.
May I just say something here? The fact that the Earth is not flat, that it is round, okay, it is something that was not obvious to people in the antiquity. So these observations, even though today they may sound, let's say, quite obvious, back in the day, they were actual research questions. So the way that people understood the cosmos and devised methods using simple math, simple as we understand them today, was ingenious. Sorry for the interruption.
Of course. So we can see a video explaining the whole situation about how Eratosthenes...
Good grammar and spelling are important, but if you want to write essays that inspire, messages that forge brighter connections, and emails that...
Let me try to share computer sound. One moment, please. So we will try to see in infographic video style how Eratosthenes did the measurement. It will take us about 2 minutes, so please watch and enjoy. Thank you.
How would you set about to measure the Earth with the mathematical knowledge and tools you already possess? A Greek named Eratosthenes did it 240 years before Christ. He was head of the great library of Alexandria in Egypt, a city built by the Greeks. He, like others, suspected that the world was round. After all, the sun and the moon were round. He had also noticed that the sun's rays fell in parallel lines. Greeks before him had divided the circle into degrees and had measured angles. With this information and a logical mind, he measured the Earth. Here is how. While visiting the city of Syene one midsummer's day, Eratosthenes noticed that the reflection of the sun could be seen in the bottom of a deep well. The sun was overhead, and the rays pointed to the center of the Earth. He remembered this, and on the next midsummer's day in Alexandria, he measured the shadow cast by an obelisk. Sunbeams travel in parallel lines, so the difference in angle had to result from the curvature of the Earth. If the angle was 1/50th of a circle, then the distance around the world must be 50 times the distance from Alexandria to Syene. With these simple tools, Eratosthenes made this almost exact measurement of the world more than 1,700 years before Magellan sailed around it. He was a friend of Archimedes. He was a mathematician and a poet, invented the sieve for finding prime numbers, was the first geographer, and corrected the calendar to the one we use today.
So after this brief, let's say, video, we can see that the nitty-gritty in order for Eratosthenes to do his measurement were the following. First of all, he needed the experimental setup, which would be mounted in 2 different locations. Okay, he needed this in order to measure, let's say, the angular difference between these 2 locations. And he also needed a way.
Of course, the alternate interior angle. So by measuring the angle between the stick and the sun rays, by finding its tangent, he could know what the angular difference between Syene and Alexandria was.
Exactly. This is what we will do today.
Yes.
Also, however, one needs to measure, let's say, the distance between the 2 locations. Back then, this was not an obvious task. Now we have, let's say, the tools of cartography, of GPS, of many ways in order to do these accurate measurements. Back then, however, distances were measured in stadia. Stadia comes from the Greek stadion, which is actually the sports center. Okay, and measuring, let's say, the dimension of this facility, you could multiply it by many times and say how many stadia is the distance between two places. In order to make an accurate measurement between Syene and Alexandria, Eratosthenes is said to have employed walkers, if I can say them correct, vimatistes, as we tell them in Greece. These are people who were trained in order to walk from one location to the other and count their steps. So they make a very, very precise, let's say, measurement of the distance between two locations by counting their steps. This is not an easy task, especially if we are talking about 800 kilometers distance, right? So let's see again how he did it. You have the circle here representing the Earth. When he did the measurement, he did it on the 21st of June. Okay, this is summer solstice.
Summer solstice, of course. And he found the angle to be 7.2 degrees. That's, of course, a 50th of the circle. And by getting these walkers to find the distance between the two cities, it was 800 kilometers estimately. If so, of course, the whole circumference of the Earth would be 50 times 800, 40,000 kilometers. And that's really close to the value that we all know today by even more, even better experiments.
Let us repeat it once again. So what do you need to do? You measure the angular distance between two locations, and you measure the distance you need to walk from one location to the other. And you form the analogy by saying that the angular distance over the full angle of a circle, which is 360 degrees, is equal to the distance you have walked, let's say, between the two locations over the whole circumference of the Earth, which you do not know. So after that, you do the calculation and you find the value. This is what we will do, okay?
Yes, so Eratosthenes' measurement was very close to the real value of the Earth's circumference, as I said. And that's, it was a really magnificent idea and yet really simple. But a little bit of geometry and a simple idea are enough for a scientific breakthrough, as we can see. To scale, Eratosthenes' estimation and actual Earth is really close.
It is about 15% off Eratosthenes, which is quite remarkable for the time that the measurement took place. Okay, so do we have any questions so far? Anything you would like to ask or discuss? Anything we didn't understand? Perfect. Okay, so what we are going to do now is to measure the world mantle. Okay, so the first step to do that, to follow Eratosthenes' footsteps, let's say, is to understand a bit what we need. Okay, so we actually need the setup. The setup, which Lucas will explain and demonstrate in detail, so I will not say a lot about that. I will just give some images, is a pole which has to be placed vertically on the surface of the Earth. Okay, this means that this one here, if you extrapolated it downwards, it should meet the center of the Earth. Okay, so if you take it, for example, and put it on the downside like this would be wrong. You always need to go vertically towards the center of the Earth. So we need the setup. As we said, here you can see the setup that we used on Thursday, okay, both in Greece and in South Africa, okay. We have a similar layout, which is a vertical pole. We make sure that this is vertical using a level in both cases. And then we need to measure very precisely the length of the pole and the length of the saddle. The next thing that we need is actually two locations. For Eratosthenes, it was
Alexandria and Syene.
Exactly. For us, it is Palini and Bloemfontein. Okay. You will see here, you will see a view of the Naval Hill Planetarium where our friends are already there. You see them from inside now. This is the location. And here is the Ελληνογερμανική Αγωγή School Observatory. I think you can see it also in the background. And also the map of Palini. If you use the globe, let's say, I just wanted to remind you a few things. I'm sure that everyone knows it, but it would be beneficial for everyone just to remember. Okay, so if you consider the Earth to be a sphere, okay, this big circle, great circle that divides it in two parts, two equal parts, let's say, is the equator. The North Pole is here, the South Pole is here, okay? If you begin to draw great circles starting from the North Pole towards the South Pole, okay, we call them meridians. And the prime meridian is the one that passes from Greenwich in the UK. These circles now that are parallel, let's say, to the equator are called parallels. Now, every circle, let's say, every location on the Earth can be identified using two coordinates, two angles, okay? The first one telling us how high, how up or down, or let's say north and south, actually, from the equator we are, is called latitude. Latitude. Okay, and the one that tells us how far we are from the prime meridian in Greenwich is longitude. Called longitude. Exactly. Longitudes usually are, let's say, explained or stated by saying that we are east or west, and latitudes that we are north or south. So you can see the values here. If we have minus here, it means south in latitude, and if we have minus in longitude, it means west, nominally. So in the measurement, actually, of Eratosthenes should be made in two locations which are located in the same meridian. Okay. I don't know how long do we have. What time is it? Okay, we have some time. So you see now that the sun's rays will fall, let's say, to the surface of the Earth, and they are parallel to each other. During the spring equinox, okay, these solar rays fall vertically to a surface which, you know, here is the equator. This would be the equator. This happens in the spring equinox. But if you go to another date, for example, today, okay, there is a location where the sun's rays will also fall vertically, but this is not necessarily, it is not the equator. Okay, why is that? Let us try to show you this using a season simulator. I don't know how clearly you can see it. Okay, so as the Earth moves around the sun, here you see the sun's rays, and here you actually see the location where they fall vertically. So if I go back a bit and go to the 21st of March, here, you will see that the sun's rays fall vertically on the equator. If you go to today's date, a bit below, here we are, they are not exactly to the equator, but a bit higher up in the northern hemisphere. If you went to June 21, again, you will see that they are vertically here in the Tropic of Capricorn, and so on. This is what defines, let's say, our seasons. So after that, let me go a bit back. Sorry for this. Okay, so here we have two locations. If I may ask, is this the equator for today? From what we heard, would anyone like to answer this question? Please unmute yourself if you want to, and be free to do that. Okay, no worries. Martha, what do you think? Is this the equator?
No, it's not.
It's a bit norther or south?
A bit norther.
A bit norther. Okay. So we have the two locations. We will measure the two angles theta and phi from Palini and from Bloemfontein. Okay, and then we will sum them. The angles are with respect to the location where the sun's rays fall vertically. We will start using step one, which is the distance between Palini and Bloemfontein using the online map maker ourselves. Okay, so I give the floor again to Manthos. Just there it is. Okay, so I think that we may need someone to give us the exact location, the exact coordinates, let's say, of Palini and of Bloemfontein in order to help us with this. Okay, Martho,
of course.
Ready?
Yes, thank you very much. So we're going to try to find the distance between Palini and Bloemfontein. Let me try to find our location.
So since we know the exact latitude and longitude of Palini, we are going to put a marker in these places.
Of course, yes. I'm going to put the first marker in our place and then in Bloemfontein. So let's say we're somewhere here, and for the second marker, okay, fine. Here we are. Yes, of course.
In order to pinpoint the exact locations with the highest, let's say, accuracy.
Yes, we need the longitude and latitude of the two locations.
And we need to zoom quite a lot.
Yes. So,
if you were zoomed out, you would place, let's say, the marker where you see Bloemfontein, but when you zoom, you may see that you are several tens or hundreds of kilometers off.
Yes, that's quite right. Now we have put the two markers, so we're ready to find the distance, actually. Mm-hmm.
The same goes for here again.
Yes. Fine. So according to our program, the distance between the two cities is 7,473.2 kilometers.
Would you keep the point 2?
0.18 to be precise.
I wouldn't keep the point 2.
Yes, I mean, yes. So for an integer precision of 7,473 kilometers.
Let me put it in the Okay. So this is the value we will be using. But also it is important, let's say, if someone wants to measure it in another way, please proceed. We propose that now you type this value to your worksheets, and we proceed from there.
Okay, yes, can you guys hear me?
Yes, perfect.
Okay, yeah, we are currently doing this measurement also here in Bloemfontein using a conventional map. So I have two eager students. I will now orientate the camera to them. So we have a map there of Africa that also includes Athens there on the top. And we are using a tape measure together with the scale of the map in order to get that distance.
Perfect.
And our measurement is?
Okay, so the measurement on the tape, what's that?
801
centimeters. Millimeters. 801 millimeters. And if we multiply that with the scale of the map, what is the distance that we get in kilometers?
Okay, 80.1 centimeters. And I multiply that, 80.1 millimeters, and I multiply that with, here's a second, 9 million.
Yeah,
9,328,000. And I get.
It's very interesting that we have two different methods to calculate the same distance, of course. Okay.
Yeah.
Okay. Okay, the value that we get is 7,472 kilometers.
Okay. So can you please repeat?
7,472 kilometers.
72. So if you see the values that we have from both, let's say maps, if I may share my screen for a moment.
Yes.
Okay. You see that the values are pretty much close.
Yes. Yeah, that's excellent. Excellent work, guys, with your measurement.
This is amazing. Now, since we are actually experimental physicists, we need to discuss a little bit the sources of error here. Okay. So the first thing is that, from my point of view, we overestimate a bit the distance between the two locations. And this happens actually because we have, apologies, because the two locations are not in the same meridian. We are off by about 300 or so kilometers. So this means that our value is a bit overestimated. So how much? This is something we can discuss at the end. Also, we need to, let's say, somehow calculate the error of our measuring, let's say, protocol. So, Professor Hoffman, what would you say? What would be the error that in using the conventional paper map? What is your estimation?
Prof. Hoffman is currently not here, so he cannot comment, but I think you can maybe give an explanation from your side.
Okay. This is something for our students to think about, and maybe you can put it in your worksheet together with your thoughts. Okay. Perfect. So, I think that we are almost there to proceed to the next step. If you are ready, we can go and actually connect with Lucas and for you to show us the experimental measurements and the setup and everything. Okay?
Okay, thank you very much.
We can take another 5 minutes, whatever you like.
Yes, our students are now going to move outside to where we can see some sun. And yeah, I will then connect with my mobile phone in order to stream live from the outside of the planetarium.
Okay, perfect.
Okay, so you guys can proceed.
So, has everyone noted these values in your worksheet? So, perfect. Let me also make everyone co-host so that everyone can share the screen if they so desire. Okay. Lucas, you are now a co-host as well. And Lucas' phone that is coming, I will also make a co-host. Yes. Also Professor Hoffman, the University of Ohio State. So I think that right now everyone is co-host. So whenever you are ready, please, you can share your screen with us, okay? Lucas, we are seeing you, but we cannot hear you yet. Perfect.
Okay, can you hear me now?
Yes, yes, perfectly.
Okay, I'm now moving to the outside of the planetarium. Okay, so this is now moving to the outside.
Okay. We definitely have to visit.
Yes, you must come and visit. It is a very nice and sunny day here at the Naval Planetarium. Just going upstairs. So this is a view of Bloemfontein. There it is.
There was a lag in your
planetarium dome here.
Okay.
Okay, can you hear me now?
Yes, yes, perfectly.
Okay, so continuing up the stairs. Here you have students. You can say hi. You're live to Greece and across the world. There's Prof. Hoffman.
Hello.
So here we have the guys responsible for the actual measurement. Sakkie van der Westhuizen. Yes.
Lucas, for some reason, we are the connection lags a bit now. We see Mariette, but the picture is stuck there. Can you hear us? Παιδιά, με ακούτε? It might be us. Okay. Okay. Let's give everyone a couple.
Hey, can you guys hear me?
Now we can hear you. We lost you for a while.
Okay, sorry. I lost my Wi-Fi network.
No problem. Let me repeat for everyone's sake that you will be explaining us in detail how you do the measurement and you will demonstrate it. But in our worksheets, we will be using Thursday's measurements, which were done from both sides during our local noons. Okay. So, Lucas, if you would like to give us an overview of the setup and how exactly are you measuring?
Okay, so just to give you a good overview, this currently I'm looking north. I'm just going to orientate my camera like that. So that's the direction in which the sun is, of course. And this is now towards the south. So you can see over here we have the stands, which are the sticks that Aristotle used. We also have a water level in order to make sure that our setup is nice and perpendicular to the ground. And then we have the shadow. It's luckily a nice clear day here in South Africa. So you can see there is the shadow of the stick. And the students, what they're now going to do is they're going to trace the edge or the tip of this shadow as the sun is going to the solar noon, where the shadow is going to be at its shortest. So we're going to measure this distance of the shadow throughout the next few minutes. And then if they have the shortest distance, then they know it's at solar noon. And then this distance from where the base of the rod is to the tip, they're going to measure with a tape measure, and also the height of the stick. And then from that, they're going to determine the angle from the sun.
Perfect.
Okay, so yeah, you guys can probably start with the measurements. What's the time currently?
Now 12:13. We are quickly measuring the.
So it's currently 12:13. Solar noon should be in Bloemfontein at about 12:23.
May I comment here on the fact that the two locations don't have the same local noon, which means that the sun, let's say, goes to its higher place in our sky at different times. This means that we actually have different longitudes. Okay, so this is quite important for us. Our difference, if I remember correct, is something like 10 minutes.
Yes, that's right.
Yes. Okay. Yeah, we are now going to start taking the measurements. We are now 10 minutes to when solar noon should occur. So we're going to coordinate it that the students take measurements every 2 minutes.
Perfect.
You make a mark at the very top of the shadow. Yes. Make it small dot. And then write the time. Or you can start. Number one. And then you write number 1 year at the start. Yes. You can do the same. We are going to announce faculty, and then you make a dot, and you mark number 1, and you write number 1 and the time. We're starting a few minutes before this is now 12:60.
The students are currently making their first mark at 12:16. A little bit of a windy day here in Bloemfontein.
Yes. May I ask you something, Professor Hoffman? Do you have penumbra? I mean, if we see your setup, do you have penumbra? Do you observe it?
Just getting the prof. I want to ask prof a question.
Yes, yes.
Hello?
Hello, can you hear me?
Yes, Manolis.
Okay, so my question is, do you observe both umbra and penumbra in your shadow?
What we will do is we will mark at the end of the dark shadow of the umbra.
But you observe penumbra also, right?
Yes. Umbra and penumbra, yeah, we can observe it.
I will zoom in that you can see. Skade yourselves. Sorry. Okay, so you can see real finely the shadow.
Yes, almost there. I think that this comes from the fact that the sun is an extended object, actually. We have a degree, let's say, diameter in the sky.
Yeah.
Okay.
Better to have a smaller stick like this one, as it's quite a sharp tipped stick.
Mm-hmm. Yes. Yes, we can see it. Now we can.
Interesting.
I think that we are quite close. In 3 minutes or so, it is your local noon. Am I correct?
Yes, you are correct. So we are going to now increase the rate of the measurement.
A fun fact is that in Greece, we changed the time yesterday to daylight saving time. But in South Africa, it doesn't change. However, our solar noons, again, are 10 minutes apart. But for us, it is 1:30. But for you, it's 12:21.
Yes, we're not exactly the same longitude. So
yeah.
Yes, you are correct. We don't observe daylight savings in South Africa. So our time didn't shift yesterday with an hour.
Okay.
I'm just moving over to my colleague's phone because my cell phone is now going to die in battery.
Okay. If I may share my screen for one moment, I just want to show something very quickly, very quickly. And just in order to explain a bit, a few things, what is happening right now. So if you assume that you are in the middle of this circle, this is the horizon, the sun rises from the east and sets in the west, and the topmost point is where we have the local noon. If you see on the shape on the left, you see actually that the sun rises, we have a longer shadow going westward, Okay, and when it culminates, we have the shortest shadow, let's
Possibly,
say.
yes, when in the local noon, exactly.
And the place where we don't have a shadow is actually where the sun's rays strike vertically the ground. Okay. So, now I can see Lucas.
Yes, sorry, you can see me. I've now on my colleague's phone, Mr. Isak van der Westhuizen. I'm just going to turn my camera around. Okay, so we are now at 12:22. So in the next minute, it's going to be solar noon. Okay. Oh, so still 12:21, sorry.
It is quite windy.
Yeah, it's quite windy. The seasons are now changing to winter here in South Africa, so you're quite lucky to get sun quite soon.
Well, this let's say, when you are doing real science, experimental science, you are subject to whether you are embedded in your environment. So you need to take all this into account. And this is the beauty of it, the wild beauty of it, let's say.
Okay, so we are now very close to the solar noon.
Because now the shadow is supposed to go longer. So you don't open your
the idea also was that today we have the measurements, as we said, from Thursday, which we will be using in the worksheets. And also, maybe if we are able to, we will have separate measurement from the data that our colleagues have acquired now in Bloemfontein, as they compare the angle, let's say, to the point where the sun's rays are vertical. So if we're lucky, we may have two measurements to compare.
So yeah, just a word of two of where we are currently. It's at the Naval Hill Planetarium. As you can see, this was originally an observatory. It was built in 1927 by the University of Michigan in the USA. The reason why they built it here in the Southern Hemisphere in Bloemfontein of all places is due to the Milky Way being perfectly clear during the winter period. Now, the observatory is now converted to a planetarium, which you saw earlier. But this planetarium is quite unique, being it's also located within a nature park. So you'll see there in the very distance, I don't know if I can maybe zoom in with the camera. Doesn't look like it, but in the distance, there's some zebra. See over there. And this nature park also has some giraffe and a few antelope. There's some antelope also there on the corner, the edge of the observatory's grounds. And this nature park is quite unique due to it being situated in the middle of the city of Bloemfontein. It's one of only 4 nature parks in the world that's located within the city itself.
This is fantastic. Fantastic location. And I guess not so much light pollution, right?
Yeah, that's the reason why the observatory closed in 1972, due to the city has expanded around the nature park. You can see already that's now in the north of Bloemfontein. That's the very edge of the city. The city is actually to the back of us. So the city has expanded around the nature park, and therefore it's no longer viable to do observation measurements from this observatory. But we still have an observatory. I can maybe orientate my camera. You will not see it with the camera, but in that direction over there, we have the Boyden Observatory that was built by the University of Harvard, also from the USA. And I also made use of the fact that the Milky Way is very good and in a good location through the winter period for observations.
Perfect, perfect. So I think that now we have more or less 20 minutes to go. So I think that if you have your measurements, we can shift to myself and Manthos, where we go step by step now to do the calculation. Okay?
Yes. I will just communicate that with the students, and then we can do the measurements. We will move inside of the planetarium and then continue from there.
Perfect, perfect.
Okay. Thank you.
So we give more or less 2 minutes for students from South Africa to go back inside the planetarium, and then we proceed to the next steps. Let me share the screen from here. Okay. So it is very important that we understand the concept of local noon. Okay. So again, in local noon, the shadow is, let's say, the shortest possible. Also, by understanding, by observing the stick, let's say, shadow during the day, you are able to discern the distance for the, let's say, from east to west, and therefore you can also help navigate yourself north, south, east, and west. So whenever you are ready, since everyone saw the process, now we are proceeding to show you, until everyone moves, let's say, let me for a moment show you. Here, what you observe is the measurement as it looked like on Thursday. Okay, this is from Palini, Greece. This is the same setup that you observe in your monitor with one of the cameras here showing it. Okay, maybe I will have to restart this one. Can you still hear me? Yes. Okay. So until everyone moves back, let me. So it's okay, perfect. So here you can see what our pinpoint the exact what our setup looked like on Thursday, the day that we are taking the measurements, using the data. So what I would like you to see is that as we proceed, this shadow moves a bit. Okay, let me, you see that it moves this way, westward. Okay, so this is the shadow as we observed it, and these are the data. You will see that we have some points there we are also taking note of, as our friends from the University of the Free State did before. Here you also see the setup from the University of the Free State on Thursday. Okay, so you have seen the demonstration of the measurement, and you have seen how we were taking the data as well. Okay, so you see how the shadow has moved from the beginning until you can see this. Okay, so let me. Is everyone ready?
Yes, our students are still finishing up the measurement outside. They are just starting though to move into the planetarium. So if you can just give us 3 to 5 minutes, it will be great.
Okay, it's just the fact that we have less than 20 minutes to go and we need to finalize the calculations. So let me share, let's say, for the students of EA that are already here, and we will repeat, let's say, the procedure when the students come back. So I will...
That's fine.
So the measurement on Thursday, the 24th of March, 2022. Okay, the local noon was on 12:31 p.m. and you will see that we have 5 measurements here. Okay, 1 minute apart from each other, centered around the local noon. So I would like the students of EA now to note these values in the worksheet. Taki, κύριε Τσουμάκη, είμαστε okay?
Yes, we are fine.
Okay.
We're writing down the measurements.
Perfect.
Okay.
So this is again the shadow length. And on 12:31, we actually measure the shortest one. Okay. So using this data that we took for you, we would like you to calculate the minimum shadow length. The pole length has been measured to be equal to 100 centimeters. Our error was of the order 1 millimeter in the measurement. Okay?
Now we will proceed with the calculations. Okay.
Yes. Let me also give you the values from Bloemfontein. Okay. From Thursday. So you see the local noon here, 12:23. Okay. You may need to take note of these measurements as well. You see the pole length, 99.6 centimeters. So please also note these numbers. Professor Hoffman, are we ready? Should I repeat this?
Yeah, Prof. Hoffman is not currently here. I think you can continue, then we'll do the calculation with our measurement that we did today. And then afterwards, we'll also compare it to the value that you got with this measurement.
Okay, just to facilitate the process, let me just put the values here. So here it was 100 centimeters, the pole length. And here, I cannot see.
71.6.
71.6 centimeters, the shadow length in Palini. And now in Bloemfontein on Thursday, we were at 99.6 centimeters and
56.7.
Thank you. If everyone has noted this, let me proceed to the next step. Professor Tsoumakis, is everything okay?
Yes, everything okay. We make the
Should I proceed?
okay.
Okay. Okay. So what we need to do now is that for the two sets of values that we have found, we need to calculate the tangent of the solar, the
angle between
the angle of incidence,
the solar rays.
The solar rays, yeah. So this is the angle. So you have to calculate first the shadow length over the stick length in two locations. So this is something that we would like to ask our students to do. You will give us the numbers a bit later. Professor Hoffman? Can you hear us?
I don't think Prof. Hoffman can hear us currently. Yeah, don't you have, I assume you have that, that links with you. I don't have it on me currently.
Could you please speak up again a bit?
Yeah, Prof. Hoffman is not currently here. Do you have that links that was measured in Bloemfontein on you? Because I don't have it currently available here at my place.
Okay.
Can you hear me?
Yes, yes, we can now.
Okay.
Yes.
The stick length, I'm not sure. I will quickly look it up. And also the shadow length for first day, but I don't have it on me. Do you have, maybe it's on you?
There is no problem with that. We just want the students to do this calculation. So first we measure tan theta, which is this over, which is 71.6 over 100, and tan phi, which is 56.7 over 99.6. Tan εφαπτωμένη in Greek. Okay. Taki, would you, when you have the numbers, could you share?
We are ready. We have count our angle, and here I have two students to take the speech. Okay.
Please do.
Thanos and Katerina.
Hello.
Hello. Yes. We found.
Guys, speak up a bit.
Okay. Yes. The tangent was 0.716.
One moment, please. Καταβάλεις εσύ. So that point 0.716.
716.
Is this the value? One moment. One moment. I just cannot hear you very well. I'm sorry for that. It's just a bit windy here, so it is our fault, let's say. So let me. Okay, so can you give us these two numbers, please, again?
So we found the tangent to be 0.716.
Perfect. Can we also calculate the tangent for Bloemfontein?
We or the.
Well, yeah, you guys can use those values in order to determine the angle.
Yeah. So it is the 56.7 over 99.6.
Anybody have an answer yet?
Yes.
What do you think this is the part of have you guys put the calculator?
Can you speak up a bit? Apologies, but I cannot hear very well because.
Anybody have an answer? We are just waiting for the students to give us an answer for that calculation.
Κύριε Τσουμάκη, θα μας δώσετε τη διαίρεση.
Yes.
Απλά δεν σας ακούω πολύ καλά.
Okay.
Το angle.
The angle is 35.6 degrees.
Όχι, για την εφαπτωμένη της
I would like first, before doing that, I would like to ask you if you could give us also tan phi, which is the Bloemfontein angle, Bloemfontein tangent, let's say.
Okay. Our students get the value for that equation of 29.69. 0.65.
Είναι 56,9 και όχι 56,7.
For today or for Thursday, Professor Hoffman?
Okay. I don't have calculate. What's the value for Thursday?
From Thursday?
Yeah, the students are just calculating quickly.
Okay, so we will keep this number. Maybe there was an offset here. Okay. So could you give us the tangent of your angle?
Okay, we calculate the angle. I agree with 29.65.
Okay, the angle is 29.65.
29.65.
Γωνία είναι αυτή, όχι εφαπτωμένη.
Let us also help repeat the calculation together. So I think we have a calculator here. Okay. So, okay. Let us do it together.
Και ήταν το πρώτο 56,9. Με το βάλω 99,6.
So, 0.571, okay? Perfect. Now, the students of EA have already offered us the value of theta. Could you please repeat?
Theta. We found the angle to be 35.60 degrees.
Perfect. Thank you very much. If we have, yeah.
The value in Bloemfontein for that angle is 29.69.
29?
29.65.
Perfect. Perfect. So you see here, if I enlarge it a bit just to help, so this is
the central angle.
35.6, 29.65, but this is not the equator. Just let me remind that, okay? So now we need to add it. So can someone give us or we can do it? Okay, so theta plus phi is 65.25. Do we all agree on that?
Yes, Bloemfontein agrees with you.
Bloemfontein?
Agrees.
Perfect. So now we have the final calculation to do. So we say that theta and phi over 360 equals the distance between Bloemfontein and Pallini over the Earth's circumference. Okay, so if we have that, let's say change this one. This is 65.25. 25. Now, if I go here, the distance between Bloemfontein and Pallini was
7,472.5.
Which one should we use? I don't think it will make much of a difference, but either way.
We can use an average.
Okay. So now we are one step from the final, let's say, calculation. Let's go. Marco, would you like to do the honors, please? Okay, stop it there. So
we have our value.
We have the value. So it is
41,227.5 estimately.
So that makes textbooks. Yes.
We have the final result for Earth circumference if you want it.
Yes, please.
Okay, so we found it to be 41,200 kilometers.
41,230. Perfect. Perfect. So let's put. Okay, so this is our value. Okay. So congratulations, everyone. Professor Hoffman, would you like me to repeat the process for your students? As a final step.
Our students agree that they understand this process quite good.
Perfect. Perfect. So we calculate that we are at 41,230 kilometers. Now, if we compare with the nominal value for the circumference of a meridian, let's do a percentage here. So it is 41,230 minus 40,009 over 40,009, okay, times 100. This means that we have a 3% offset from the nominal value. So we are doing, let's say, 5 times better than Eratosthenes himself. Yes. Congratulations, everyone.
That's a really good approximation.
So I think that we have the numbers. I will stop sharing I will thank everyone from my part, and I will give the floor to you if you would like to comment, to share, to discuss anything.
Okay, thank you very much, Mael. Can I maybe share my screen?
Yes, please.
Okay, so I just prepared a quick PowerPoint presentation of the sources of the errors. Okay, can you see my screen over there? The sources of some errors for this calculation. So first of all, one thing that we noticed when we looked at the shadow of the poles, that the shadow was not very well defined. And the reason for that is, of course, the sun is not a point source. It has a width to it in our day sky. So that causes this shadow to be a little bit blurry. So that was the source of most of the errors, I suspect, in this calculation. Another thing to consider is the refractive index of the atmosphere is different to that of space. As you know, of Snell's law, light bends when it goes from one medium to the other. So that causes, if you look at the schematic of the Earth and the sun, you can see how the sun's rays are being bent. And you observe then the sun in a different part in the sky to where it really is. The great thing about this is that you actually see a sunrise before the sun has risen due to the atmosphere bending the light. And also you see the sun set after the sun has already set. Another thing is that the Earth is not entirely spherical. It is a little bit, it is a higher diameter at the equator. It has a diameter of 40,075 kilometers at the equator, while when you measure it via the poles, it has a diameter or a circumference of 40,008 kilometers. That's due to the Earth's rotation that causes the centrifugal forces, causes the Earth to squish a little bit out at the sides. Now, it's quite astonishing to see that this value of the Earth measured from the poles is this close to 5,000 kilometers. And that is no coincidence, since the definition of a meter is originally based on the length from the pole to the equator via Paris. So here, this is how the meter was originally defined. By the length, it is from the pole to the equator divided by 10 million. And that is where the standard for the meter length comes from. Of course, our technology has increased over a couple of years that we can measure this distance much more accurately. That's why the value is not exactly 40,000 kilometers. However, this was originally when the French Revolution occurred, where the definition of the meter came from. Okay, that's all from my side. Over to you, Emmanuel.
From our side, I would like to say that the main source, let's say, of uncertainty that we had was first the distance calculation, which we said that it was offset. Okay. The second one is the fact that always it is quite difficult to measure the exact point where we shift from umbra to penumbra. Therefore, you have an error of the order of a few millimeters in the calculation of the shadow. And I think that these are mainly these. I think that together we accomplished something fantastic because we got much better than Eratosthenes, actually. So I would like to give the floor to the students if they have any questions or remarks or anything they would like to comment. And I think that we are quite close to ending, let's say, today's event. So I give the floor to everyone who would like to share and discuss. So.
Okay, dear colleagues, all the activity was fantastic, superb. We enjoyed this activity and hope to do this again next year. in better conditions and better weather here in Greece. Thank you very much.
Thank you. Thank you very much. Professor Hoffman? Lucas?
I don't think we have any questions from this side. We also just like to thank you for being part of this. And yeah, we hope to continue closely with you guys in the future regarding this and other projects.
Okay.
Prof. Hoffman is just going to say something officially.
Yes.
Okay. Hello, Manolis. It was fantastic to experience the collaboration between a group of learners in Athens in Greece and in Bloemfontein, South Africa. We have, before last year, we have been visited in Bloemfontein by the Consul General of Greece on 2 occasions. So we have established during the last year and a half a very good collaboration with you. I'm proud of the learners who are here during the school vacation. It was really good to see them measuring out there. That is, to measure in science is a very important thing. It lies at the heart of science. And of course, to do something with those measurements and to repeat a measurement that was done more than 2,000 years ago, that brings that history, which is important to have that insight of what people already were able to do a long time ago with very limited technology, but just using imagination and mathematics. Okay, and the level of mathematics that we had to use, I think it's about grade 10 in school, where you learn about trigonometry, maybe grade 11. So it's not advanced geometry, but still it needs some focus and accuracy. Thank you very much to the colleagues from Science for the Future, Mariette over here, and Dr. Kobus van Breda there in the back. They are a well-organized group, and they arranged for the learners to be here today. It is a fantastic contribution, and to my 2 young colleagues, Saki on the Westhuizen, you won't believe it, but it's somewhere there in the dark, over there, and Lucas, thank you very much for your contribution today. It is really hard, a good experience. Okay.
Thank you all. Thank you all very much.
Thank you very much. Thank you.
From our part, I would like to thank Manthos, Professor Panagiotis Soumakis, the technical team who supported us, Panos, Lazaros, and all the students who were with us. Thank you, everyone, and let's set our date for next year. Okay. Bye-bye.
Bye.
Bye, everyone. Thank you to all the students from South Africa as well. Bye. Bye.